Giant gas planets. We've all heard and know a little bit about them. But what if I told you there is a deeper mystery that lies within these gas planets that have not been taught in schools? We begin deep within the atmosphere of Neptune. There exists a phenomenon that defies everything we thought we understood about planetary weather. Methane crystals rain downward through layers of crushing pressure, and as they descend deeper into the planet's interior, the temperature and pressure become so extreme that these simple carbon and hydrogen compounds undergo a transformation. The carbon atoms are squeezed free from the hydrogen, and under pressures exceeding 2 million times Earth's atmospheric pressure, these carbon atoms crystallize into something unexpected: diamonds. Not small diamonds, but gemstones potentially the size of cars, falling slowly through an ocean of liquid metallic hydrogen, creating what scientists have nicknamed diamond rain. This isn't science fiction or wild speculation. This is a prediction based on our best understanding of high-pressure physics and the composition of ice giant atmospheres. Laboratory experiments have successfully recreated the conditions necessary for this process, and the mathematics supports it. Somewhere inside Neptune, and likely inside Uranus as well, there may be a layer where diamond hailstorms are a constant reality, where precious gemstones drift downward through an alien sea, accumulating over millions of years into massive deposits that will never be mined, never be worn, never be seen by human eyes. The gas giants and ice giants of our solar system harbor secrets that challenge our understanding of physics, chemistry, and planetary science. These worlds are not simply larger versions of Earth with thicker atmospheres. They are fundamentally different beasts, operating under rules that seem alien to anyone, familiar only with rocky planets. Jupiter, Saturn, Uranus, and Neptune represent 4 variations on a theme, each one unique, each one strange in its own way, and each one hiding processes and phenomena that educational systems rarely explore in depth. Consider the internal structure of Jupiter. Most people learn that Jupiter is a gas giant, made mostly of hydrogen and helium, and the mental image that forms is often of a planet that is gaseous all the way through, like a ball of air. But this picture is deeply misleading. If you could somehow survive a journey into Jupiter's depths, descending through layer after layer of increasingly dense atmosphere, you would eventually reach a point where the very concept of gas becomes meaningless. The pressure at these depths is so immense that hydrogen stops behaving like a gas entirely. It doesn't become a liquid in the way water is liquid. Instead, it transforms into a state of matter that doesn't exist naturally anywhere on Earth. Liquid metallic hydrogen. In this exotic state, hydrogen atoms are squeezed so tightly together that their electrons are stripped away and can move freely, just like electrons in a metal wire. This gives the hydrogen electrical conductivity, turning the interior of Jupiter into an enormous electrical generator. The planet's rapid rotation, completing one full spin in less than 10 hours, causes this metallic hydrogen ocean to swirl and flow, generating the most powerful magnetic field of any planet in the solar system. This magnetic field is so strong that if you could somehow make it visible, Jupiter would appear larger than the full moon in Earth's sky, even from our distance of hundreds of millions of miles away. The magnetosphere extends millions of miles into space, capturing charged particles and creating radiation belts so intense that they can damage spacecraft electronics. Every probe that has visited Jupiter has had to be specially hardened against this radiation. And even then, the environment eventually degrades sensitive instruments. But below even the layer of metallic hydrogen, there may be something stranger still. The core of Jupiter, if it exists as a distinct entity, is likely not a simple ball of rock and metal like Earth's core. Instead, current models suggest it might be a fuzzy core, a region where the distinction between the rocky metallic core material and the surrounding metallic hydrogen becomes blurred. The extreme temperatures, potentially reaching 30,000 degrees Fahrenheit, combined with pressures millions of times greater than Earth's atmospheric pressure, create conditions where the normal rules about what is solid and what is liquid break down. Materials that would never mix under normal conditions might form strange alloys and compounds. The core might not have a sharp boundary, but rather a gradual transition zone where rock and metal dissolve into the metallic hydrogen, like sugar dissolving in water. Except the solution is hot enough to vaporize any known material, and under such extreme pressure that our intuitions about matter completely fail. Saturn presents its own mysteries, particularly in the realm of its atmosphere. While Jupiter's great red spot gets most of the attention, a massive storm that has raged for centuries, Saturn hosts a peculiar phenomenon that appears and disappears on a schedule. Roughly every 30 Earth years, corresponding to one Saturnian year, a massive storm erupts in Saturn's northern hemisphere. This storm, called the Great White Spot, grows to encompass a region larger than Earth's diameter, creating turbulence that can be seen even through amateur telescopes. The storm rages for months before gradually dissipating, only to return like clockwork 3 decades later. Scientists are still working to understand what triggers these periodic outbursts. The leading theory involves seasonal changes as Saturn orbits the Sun, with different parts of the planet receiving varying amounts of sunlight over its long year. But the exact mechanism that causes the sudden explosive growth of these storms remains an active area of research. What makes this even more intriguing is what happens in Saturn's upper atmosphere during normal, non-stormy periods. High above the cloud tops, in the ionosphere, complex organic molecules form through reactions driven by ultraviolet light from the Sun. These molecules, called tholins, are similar to the compounds that scientists believe may have been precursors to life on early Earth. On Saturn, these orange-brown tholins drift slowly downward, giving some of Saturn's atmospheric features a distinct coloration. As they descend into deeper, hotter regions of the atmosphere, they break apart and are recycled. It's a chemical cycle that turns Saturn into a giant laboratory for organic chemistry, creating and destroying complex molecules in an endless process that has continued for billions of years. The ring system of Saturn, while visually stunning, also presents puzzles that weren't taught in school. Most educational materials mention that the rings are made of ice particles ranging in size from grains of sand to house-sized boulders. What they often don't explain is how impossibly thin these rings are relative to their diameter. If you could shrink Saturn's rings down to the size of a sheet of paper in diameter, they would be thousands of times thinner than that paper. Despite spanning more than 200,000 miles from inner edge to outer edge, the main rings are typically only about 30 feet thick. This extreme thinness means that the rings are essentially a two-dimensional structure, a vast disk of orbiting particles that rarely collide vertically but constantly interact horizontally. Even stranger is the question of the ring's age. For decades, scientists assumed that Saturn's rings were ancient, formed at the same time as the planet itself 4.5 billion years ago. But recent data from the Cassini spacecraft, which orbited Saturn for 13 years before deliberately plunging into the planet's atmosphere in 2017, suggests something different. By measuring the mass of the rings and analyzing how much dust and debris has contaminated them, scientists calculated that the rings might be surprisingly young, perhaps only a few 100 million years old. This would mean that the rings formed relatively recently in cosmic terms, possibly from the destruction of a small moon that wandered too close to Saturn and was torn apart by tidal forces. If this is true, then Saturn's rings are a temporary feature, and they won't last forever. Over the next few 100 million years, the rings will gradually disappear as particles spiral inward and fall into Saturn's atmosphere, or are knocked outward by collisions and escape the planet's gravitational influence. Future astronomers billions of years from now might look at Saturn and see only a faint reminder of the magnificent ring system that existed in the early 21st century. Uranus rotates on its side, tilted 98 degrees relative to its orbital plane. This extreme axial tilt means that the planet's poles experience 42 years of continuous sunlight, followed by 42 years of total darkness, as Uranus completes its 84-year journey around the Sun. This bizarre orientation affects everything about the planet, from its weather patterns to its magnetic field behavior. The leading theory for this tilt involves a catastrophic collision early in the solar system's history. A massive object, perhaps as large as Earth, may have struck Uranus with enough force to knock it over. Such an impact would have delivered tremendous energy, melting much of the planet's interior and potentially ejecting material that later coalesced into some of Uranus's moons. But the tilt isn't the only strange thing about Uranus. Its magnetic field is deeply peculiar. On Earth, and on most other planets, the magnetic field is roughly aligned with the planet's rotation axis, with the magnetic poles located near the geographic poles. Uranus doesn't follow this pattern. Its magnetic field is tilted nearly 60 degrees away from its rotational axis, and the center of the magnetic field doesn't even pass through the planet's center. It's offset by about 1/3 of the planet's radius. This creates a lopsided, wobbling magnetic field that tumbles around as the planet rotates. Every 17 hours, as Uranus completes one rotation, the magnetic field orientation changes dramatically for any object in the vicinity. This would make navigation using a magnetic compass completely impossible near Uranus, as the field direction would be constantly shifting. Scientists aren't sure why Uranus has such an unusual magnetic field. One possibility is that the field is generated not deep in the planet's core, but in a relatively shallow layer of electrically conductive ices, perhaps a layer of ammonia-rich water compressed into an ionic state where charged particles can move freely. If this is the case, then the geometry of this conducting layer might naturally produce an offset, tilted field. Another possibility is that we happened to observe Uranus during a period when its magnetic field is reversing, similar to how Earth's magnetic field has reversed many times throughout geological history. During a reversal, the field can become chaotic and disorganized before settling into a new configuration. However, magnetic reversals on planets are thought to occur over thousands or millions of years, and the chances of catching Uranus in the middle of such an event seem low. Neptune, the outermost planet, shares many characteristics with Uranus. Both are classified as ice giants rather than gas giants because their compositions are dominated not by hydrogen and helium, but by heavier elements like water, methane, and ammonia in various phases. Neptune's atmosphere contains more methane than Uranus, which is why Neptune appears as a deeper, richer blue, while Uranus has a pale cyan tint. The methane absorbs red light and reflects blue, giving both planets their distinctive colors. But Neptune is far more active than Uranus, despite being farther from the Sun and receiving less solar energy. When Voyager 2 flew past Neptune in 1989, it discovered a storm system called the Great Dark Spot, an Earth-sized vortex, similar in some ways to Jupiter's Great Red Spot. This storm was accompanied by high-altitude clouds of methane ice crystals that cast shadows on the cloud deck below, something that had never been observed on any other planet. The wind speeds on Neptune are the highest measured anywhere in the solar system, reaching up to 1,500 miles per hour. These supersonic winds exist in an atmosphere that receives only about 1% of the sunlight that Earth receives, which raises a profound question. Where is the energy coming from to drive such violent weather? The answer appears to be internal heat. Neptune radiates more than twice as much energy into space as it receives from the sun. This means there must be a powerful internal heat source, but scientists aren't entirely sure what it is. One possibility is leftover heat from the planet's formation, still slowly escaping after 4.5 billion years. Another possibility is that the heat comes from chemical processes in the planet's interior, perhaps from the separation of different materials as heavier elements sink toward the core. The diamond rain phenomenon could actually contribute to this heating, as the crystallization of carbon releases energy. Whatever the source, this internal heat drives convection currents that power Neptune's ferocious winds and create the most dynamic weather system of any planet in the outer solar system. The magnetic field of Neptune is equally strange as that of Uranus. It too is tilted roughly 47 degrees from the planet's rotation axis, and it too is offset from the planet's center. When Voyager 2 measured Neptune's magnetic field and found it shared these characteristics with Uranus, it essentially ruled out the possibility that Uranus's weird magnetic field was due to a magnetic reversal or some other temporary condition. Instead, both ice giants appear to have fundamentally different magnetic field generation mechanisms compared to Earth, Jupiter, and Saturn. This similarity between Uranus and Neptune strongly suggests that the offset tilted magnetic fields are a natural consequence of ice giant interior structure, where the conducting layers that generate the field are relatively shallow and geometrically constrained in ways that don't occur in gas giants or rocky planets. The temperature structure of these planets reveals more surprises. You might expect that the cloud tops of the outer planets would be uniformly cold, and they are certainly frigid by Earth standards. But there are variations that scientists are still working to explain. Jupiter's upper atmosphere has hotspots, regions where temperatures are significantly higher than in surrounding areas. These hotspots appear to be locations where atmospheric gases are descending, getting compressed and heated in the process, similar to how a bicycle pump gets warm when you compress air. At these locations, there are fewer clouds blocking the view to deeper levels, allowing infrared telescopes to peer deeper into Jupiter's atmosphere. Saturn has a warm polar vortex at its north pole, a vast hexagonal-shaped storm system where each side of the hexagon is wider than Earth's diameter. The hexagon has been observed to be remarkably stable, maintaining its shape for decades. Inside this hexagon is a hurricane-like storm with an eye at the exact North Pole. The winds of the hexagon race around the pole at speeds of more than 200 miles per hour, and the entire structure appears to be a standing wave pattern, a stable configuration where the atmospheric flows balance in just the right way to maintain the hexagonal shape. No other planet has anything quite like Saturn's hexagon, and fully explaining its formation and persistence remains a challenge. The great red spot of Jupiter, while famous, is shrinking. Historical observations show that the storm was much larger in the 1800s than it is today. When astronomers first studied it in detail in the mid-19th century, the great red spot was wide enough to fit 3 Earths inside it. Today, it's barely large enough to fit 1 Earth. The storm is contracting at a measurable rate, and if this trend continues, it might disappear entirely within a few decades. Why the storm is shrinking is unclear. It might be related to changes in Jupiter's internal heat flow, or changes in the atmospheric jet streams that surround and stabilize the storm. Or it could be part of a long cycle where the storm contracts and expands over centuries. Without continuous observations stretching back thousands of years, we can only speculate about the long-term behavior of Jovian storms. Jupiter's moon Io, while technically a moon rather than part of the planet itself, plays a crucial role in Jupiter's magnetosphere. Io is the most volcanically active body in the entire solar system, with hundreds of active volcanoes constantly erupting. These eruptions spew sulfur and sulfur dioxide into space at such a rate that Io is surrounded by a donut-shaped cloud of ionized gas called the Io plasma torus. This torus is trapped in Jupiter's magnetic field and rotates with the planet. The material from Io gets accelerated to enormous speeds by Jupiter's rapid rotation, creating a high-energy environment that bombards not only Io itself, but also the other Galilean moons. Europa, Ganymede, and Callisto all receive significant radiation doses from particles originating at Io. This radiation complicates any future missions to explore these moons, particularly Europa, which is thought to have a subsurface ocean that might potentially harbor life. Speaking of Europa, this moon's interaction with Jupiter provides a beautiful example of tidal heating. Europa orbits Jupiter every 3.5 Earth days, and as it does, Jupiter's immense gravity raises tides in the moon's interior. If Europa orbited in a perfect circle, these tides would rise and fall in a regular, predictable way, and the moon would quickly settle into a stable configuration where the same part of Europa always faces Jupiter. But Europa's orbit is slightly elliptical, made so by gravitational interactions with the other Galilean moons. This means that the strength of Jupiter's gravitational pull on Europa changes throughout the orbit. Sometimes Jupiter pulls harder, sometimes less hard. This varying tidal force causes Europa's interior to flex and deform continuously, like squeezing a rubber ball over and over. This flexing generates heat through friction, enough heat to keep a global ocean of liquid water beneath Europa's icy crust. Without this tidal heating, Europa would be frozen solid, and the ocean that makes it such an intriguing target in the search for extraterrestrial life would not exist. Saturn's moon. Enceladus experiences similar tidal heating, though on a smaller scale. Enceladus is tiny compared to Europa, only about 300 miles in diameter, yet it too has a subsurface ocean. The evidence came from the Cassini spacecraft, which discovered that Enceladus is spraying jets of water vapor and ice particles into space from cracks near its south pole. These jets, or geysers, erupt continuously, feeding Saturn's E-ring with fresh ice particles. By flying through these plumes and analyzing their composition, Cassini found not just water but also salts, organic molecules, and even molecular hydrogen. The presence of hydrogen is particularly intriguing because it could provide an energy source for microbial life if any exists in Enceladus's ocean. The hydrogen likely comes from hydrothermal vents on the ocean floor, where hot water reacts with rock, similar to the hydrothermal vents on Earth's ocean floor that support thriving ecosystems despite the absence of sunlight. The moons of Uranus are oddly dark and reddish, particularly the inner moons. These moons orbit within Uranus's magnetosphere and are constantly bombarded by charged particles. This radiation processing gradually changes the surface chemistry of these moons, creating dark, carbon-rich materials. The largest moon, Titania, shows evidence of past geological activity. Its surface has enormous canyons that suggest the moon's interior froze and expanded at some point in its history, cracking the crust. But why Titania would have been warm enough to have a liquid interior that could later freeze is another mystery. Perhaps early in its history, radioactive decay or tidal heating provided enough warmth, but over time these heat sources diminished, and the moon slowly froze. Neptune's moon Triton is perhaps the strangest large moon in the solar system. It orbits Neptune backward in what's called a retrograde orbit. Every other large moon in the solar system orbits its planet in the same direction that the planet rotates. Not Triton. This backward orbit is strong evidence that Triton didn't form alongside Neptune, but was instead captured from elsewhere in the solar system. Triton is remarkably similar in size and composition to Pluto, and it's likely that Triton was once a dwarf planet in its own right, wandering the outer solar system, until it happened to pass too close to Neptune and was captured by the planet's gravity. But the capture process would have been violent and chaotic. When Triton was first captured, its orbit would have been highly elliptical, bringing it very close to Neptune and then swinging it far away. The tidal forces during the close approaches would have been tremendous, heating Triton's interior through tidal flexing. Over millions of years, these tidal interactions gradually circularized Triton's orbit, dissipating orbital energy as heat inside the Moon. This process likely melted much of Triton's interior, erasing any geological features that existed before capture. Today, Triton's orbit is nearly circular, and the tidal heating has diminished, but the Moon still shows signs of relatively recent geological activity. Voyager 2 discovered nitrogen geysers on Triton's surface, plumes of nitrogen gas and dark organic particles erupting from beneath the surface and rising several miles into the thin atmosphere. These geysers suggest that even now, billions of years after capture, Triton may have pockets of liquid or slushy material beneath its frozen crust. The rings of Jupiter, Uranus, and Neptune are far less impressive than Saturn's, but they exist and have their own characteristics. Jupiter's ring system is faint and made primarily of dust rather than ice. The dust appears to come from small moons embedded within and near the rings. Micrometeorite impacts on these moons kick up dust particles, which then spread out into gossamer sheets encircling Jupiter. Without the constant resupply from moon impacts, Jupiter's rings would disappear in a cosmologically short time. Uranus's rings were discovered by accident in 1977, when astronomers were watching Uranus pass in front of a distant star. Before the planet itself blocked the star's light dimmed several times in a symmetrical pattern. This indicated that there were rings surrounding Uranus, blocking the starlight. Later, observations confirmed the existence of 13 distinct rings, most of them narrow and dark. Unlike Saturn's rings, which are bright and icy, Uranus's rings are made of dark material, possibly organic rich compounds similar to soot. The rings are also kept in place by shepherd moons, small satellites whose gravity prevents the ring particles from spreading out. Neptune's rings are even fainter and include strange arc-like structures. While most ring systems are uniform all the way around the planet, Neptune has sections where the rings are much denser, creating bright arcs. These arcs were initially puzzling because mathematically, ring particles should spread out evenly around a planet over time. The discovery of small moons near the ring arcs provided an explanation. These moons' gravitational influence traps ring particles in specific locations, creating the arcs. However, the full dynamics of how these arcs remain stable over time are still being studied. The chemical composition of the gas giants reveals information about the early solar system. Jupiter and Saturn captured most of their material directly from the solar nebula, the cloud of gas and dust from which the sun and planets formed. As a result, their compositions closely match that of the sun itself, with hydrogen and helium dominating, and heavier elements present in small amounts. By measuring the abundances of different elements in Jupiter's and Saturn's atmospheres, scientists can learn about the composition of the solar nebula and test theories about how the solar system formed. One surprising finding is that Jupiter has more heavy elements than expected. The atmosphere contains enrichments of elements like carbon, nitrogen, and sulfur compared to the Sun. This suggests that in addition to capturing gas from the nebula, Jupiter also accreted significant amounts of solid material, possibly in the form of icy planetesimals similar to comets. These solid materials would have enriched Jupiter's composition in heavier elements. The presence of these elements also affects the planet's interior structure and might contribute to the formation of that fuzzy core. Saturn has a similar enrichment pattern, though not as extreme as Jupiter's. The differences between Jupiter and Saturn might reflect their formation locations and timings. Jupiter, being closer to the Sun, formed earlier and had access to more material. Saturn formed farther out and later, capturing less gas overall. By the time Saturn was forming, the solar nebula might have already been dissipating, limiting how much hydrogen and helium it could accumulate. There's also a fascinating question about planetary migration. The current arrangement of the solar system, with rocky planets close to the Sun and gas and ice giants farther out, seems orderly, but it might not reflect the original configuration. The NICE model, named after the French city where it was developed, proposes that the giant planets formed closer together and closer to the Sun than they are today. Early in the solar system's history, these planets migrated outward due to gravitational interactions with a disk of icy planetesimals beyond Neptune's current orbit. As the planets moved outward, they scattered these planetesimals, some inward toward the inner solar system, and some outward into what's now the Kuiper belt. This migration may have triggered the late heavy bombardment, a period about 4 billion years ago, when the inner solar system, including Earth and the Moon, experienced a dramatic increase in asteroid and comet impacts. According to the NICE model, Jupiter migrated inward slightly before reversing direction and moving outward again. Saturn, Uranus, and Neptune all migrated substantially outward. This migration rearranged the entire outer solar system and may explain several otherwise puzzling features, such as the orbital properties of Kuiper belt objects and the Trojan asteroids that share Jupiter's orbit. If the NICE model is correct, then the gas and ice giants we see today are not in their original positions, and the early solar system was a much more chaotic and dynamic place than a simple snapshot of the current planetary positions would suggest. The formation of the gas giants themselves is still not fully understood. The traditional model, called core accretion, proposes that the planets began as rocky, icy cores about 10 times Earth's mass. Once these cores reached sufficient size, their gravity became strong enough to rapidly capture gas from the surrounding solar nebula, growing into gas giants. This model works well for explaining Jupiter and Saturn, but it struggles with Uranus and Neptune. At their distances from the Sun, the solar nebula would have been so sparse that building even a 10-Earth mass core would have taken longer than the nebula's lifetime. The nebula likely dissipated after only a few million years, yet core accretion models suggest Uranus and Neptune needed tens of millions of years to form. One solution is that Uranus and Neptune didn't form where they are now. They might have formed closer to Jupiter and Saturn, where material was more abundant, and then migrated outward to their current positions. This idea fits well with the NICE model and could explain why the ice giants have less hydrogen and helium than the gas giants. They began migrating outward before they could fully capture a massive gas envelope. An alternative model called disk instability proposes that gas giants can form much more rapidly through a direct gravitational collapse of dense regions in the solar nebula. If the nebula becomes locally unstable, it can fragment into clumps that collapse under their own gravity, forming a gas giant in just a few thousand years. This model could explain how giant planets form quickly before the nebula dissipates, but it has difficulty explaining the observed core masses inside Jupiter and Saturn. If these planets formed by direct collapse, they shouldn't have massive cores, yet evidence suggests they do, The truth might involve aspects of both models. Perhaps giant planets begin with a rapidly formed core from disk instability, which then accretes additional material through core accretion. Or perhaps different planets form through different mechanisms, depending on their distance from the star and the local conditions in the nebula. Observations of exoplanets, planets orbiting other stars, have revealed that gas giants are common throughout the galaxy, but they come in a bewildering variety. Some are larger than Jupiter, but orbit closer to their stars than Mercury orbits the Sun, completing an orbit in just a few days. These hot Jupiters can't have formed where they are, as planets that close to a star would never be able to accumulate enough material to become gas giants. They must have formed farther out and migrated inward, possibly through gravitational interactions with the protoplanetary disk or with other planets. Some exoplanets are even stranger. There are planets in between gas giants and ice giants in mass, called mini-Neptunes, which appear to be extremely common around other stars, yet are completely absent from our own solar system. We have no planets between Earth, at 1 Earth mass, and Uranus, at 14.5 Earth masses. This gap represents a missing category of planet in our solar system, and understanding why this gap exists could provide important clues about planet formation. One possibility is that mini-Neptunes did form in the early solar system, but were ejected during the chaotic migration phase. Another possibility is that something about the conditions in our solar nebula prevented planets of that mass from forming. The discoveries of exoplanets have forced scientists to rethink many assumptions about planetary systems. For decades, our solar system was the only example we had, and it was tempting to think that other systems would be similar. But the reality is far more diverse. Giant planets can exist on all kinds of orbits, from scorching hot orbits close to their stars to distant, frigid orbits even farther out than Neptune. Some are alone. Some are in tightly packed systems with multiple giant planets. Some have highly elliptical orbits, and some are in binary star systems where the dynamics are completely different from anything in our solar system. Studying exoplanets also helps us understand our own giant planets better. By comparing Jupiter and Saturn to hot Jupiters, or Uranus and Neptune to exoplanetary mini-Neptunes, scientists can test whether the physical processes we think govern our solar system's planets also apply elsewhere. So far, the answer seems to be yes, but with caveats. The same basic physics of gravity, thermodynamics, and fluid dynamics applies everywhere, but the specific outcomes depend sensitively on initial conditions, which vary widely from system to system. The atmospheres of giant planets are laboratories for extreme meteorology. On Earth, weather is driven by solar heating, which warms the surface and causes air to rise, creating convection. Giant planets have similar processes, but with added complications. Their rapid rotations create powerful Coriolis forces that organize weather into banded patterns. Jupiter's cloud bands, alternating light and dark stripes, are jet streams where winds blow in opposite directions in adjacent bands. These jets are remarkably stable, persisting for decades or longer. The light bands, called zones, are regions where gases are rising and cooling, forming high-altitude clouds. The dark bands, called belts, are regions where gases are sinking and warming, evaporating clouds and revealing deeper, darker layers. The exact mechanism that maintains these jets is still debated. On Earth, jet streams are powered by temperature differences between the equator and the poles. On Jupiter, the internal heat flow and the rapid rotation seem to play larger roles. Computer simulations of Jupiter's atmosphere can reproduce banded structures, but matching the observed number of bands, their widths, and their wind speeds requires careful tuning of the model parameters. This suggests that there are subtle details of Jupiter's interior structure and heat transport that we don't yet fully understand. Saturn's atmosphere is similar, but has additional complexity due to its lower gravity and deeper atmosphere. The bands on Saturn are less distinct than on Jupiter, and the colors are more muted. This might be because Saturn's atmosphere has more haze, or because the cloud layers are at different depths. Saturn also has enormous storms that appear suddenly and grow rapidly. The great white spots that appear every 30 years can grow to span the entire circumference of the planet within weeks. These storms create turbulence that disrupts the banded structure temporarily. But once the storm dissipates, the bands reform, indicating that the underlying jet streams are persistent features driven by processes deep in the atmosphere. On Uranus and Neptune, the weather is more difficult to observe because these planets are so far away and have fainter features. But when storms do appear, they can be quite prominent. The great dark spot on Neptune, observed by Voyager 2, was an anticyclonic storm similar to Jupiter's Great Red Spot. However, when the Hubble Space Telescope looked for the Great Dark Spot a few years later, it had vanished. New dark spots have appeared in different latitudes since then, suggesting that these storms on Neptune are relatively short-lived compared to the centuries-long Great Red Spot. This difference might be due to Neptune's stronger internal heat source, which could destabilize large vortices over time. The clouds themselves on these planets are made of different materials depending on the temperature and pressure at a given altitude. On Jupiter and Saturn, the uppermost clouds are ammonia ice crystals, white and reflective. Below that are clouds of ammonium hydrosulfide, which have a brownish color. Deeper still are water clouds, but these are usually hidden beneath the upper layers. The various shades of brown, red, and orange seen in Jupiter's clouds come from trace chemicals, possibly including sulfur compounds, phosphorus compounds, or complex organic molecules created by lightning and ultraviolet radiation. The exact chemistry is still uncertain because the concentrations of these coloring agents are very low, and laboratory experiments trying to recreate Jupiter's cloud chemistry don't perfectly reproduce the observed colors. On Uranus and Neptune, the clouds are primarily methane ice crystals. Methane condenses at the cold temperatures found in their upper atmospheres, forming bright white clouds that float above a hazy layer of photochemical smog. This smog is made of hydrocarbons and nitriles, molecules created when ultraviolet light breaks apart methane molecules, and the fragments recombine into more complex forms. Over time, these molecules grow larger and more complex, eventually forming particles that drift downward. This process gives the upper atmospheres of Uranus and Neptune a layered structure, with clear regions alternating with hazy regions. Lightning on giant planets is different from lightning on Earth. On Earth, lightning forms in water clouds when ice particles collide, separating positive and negative charges. The charges build up until a discharge occurs, creating a lightning bolt. On Jupiter and Saturn, lightning can form in water clouds deep in the atmosphere, where temperatures and pressures are similar to Earth's surface conditions. Spacecraft have detected radio emissions from these lightning bolts, even though the flashes themselves are usually hidden beneath upper cloud layers. Occasionally, gaps in the clouds allow a direct view of lightning, and spacecraft have captured images of glowing flashes deep in Jupiter's atmosphere. Neptune also has lightning, detected by Voyager 2 as radio bursts. Given that Neptune's atmosphere is mostly hydrogen and helium, with only a small amount of methane and water, the mechanism for charge separation might be different. It's possible that the lightning forms in water clouds at great depth, or perhaps in methane clouds at higher altitudes, where temperatures are cold enough for methane to condense. One of the most enduring mysteries about giant planets is their heat budgets. Jupiter, Saturn, and Neptune all radiate more heat than they receive from the Sun. Jupiter radiates about 67% more energy than it absorbs. Saturn radiates about 78% more. Neptune radiates about 2.6 times as much energy as it absorbs. Uranus, strangely, does not have a significant excess of internal heat. It radiates almost exactly the amount of energy it receives from the Sun, with only a small, detectable excess. The explanation for Jupiter and Saturn is thought to be leftover heat from their formation. When these planets formed, the gravitational energy released as material fell inward heated the planet's interiors to very high temperatures. Over billions of years, this heat has been slowly leaking out into space. Additionally, helium raindrops might be forming deep inside Saturn. Helium is slightly denser than hydrogen, and under the pressure and temperature conditions deep inside Saturn, helium droplets might form and rain downward toward the core. This process releases gravitational potential energy, which gets converted to heat, contributing to Saturn's internal heat output. Neptune's strong internal heat source is harder to explain. Neptune is smaller and less massive than Jupiter and Saturn, so it should have cooled off faster and should have less leftover primordial heat. Yet Neptune radiates more heat per unit area than any other giant planet. The diamond rain hypothesis is one possible explanation. As methane in Neptune's atmosphere is broken down by temperature and pressure, the carbon crystallizes into diamonds. As these diamonds sink toward the core, they release gravitational energy, which heats the surrounding material. This process could sustain Neptune's heat output over billions of years. Uranus's lack of a significant internal heat source is deeply puzzling. All models predict that Uranus should be radiating more heat, similar to Neptune. One possibility is that Uranus's interior is poorly mixed, with heat trapped in the lower layers and unable to efficiently reach the surface. If Uranus's interior is stably stratified, with denser material below and lighter material above, convection would be suppressed. Heat would have to escape through conduction, which is much slower. This could result in a hot interior, but a cold surface, giving the appearance that Uranus lacks internal heat. Another possibility relates to the giant impact that knocked Uranus on its side. If the impact mixed the interior thoroughly, it might have accelerated the cooling process, allowing Uranus to lose its primordial heat faster than Neptune. Alternatively, the impact might have deposited so much energy that it melted the interior, and the subsequent cooling and solidification could have created the stable layering that prevents efficient heat transport today. The study of giant planets also extends to their auroras. On Earth, auroras occur when charged particles from the Sun are funneled by Earth's magnetic field toward the poles, where they collide with atmospheric gases and cause them to glow. Giant planets have much stronger magnetic fields and much larger magnetospheres, so their auroras are correspondingly more powerful. Jupiter's auroras are the brightest in the solar system, emitting more energy in ultraviolet and X-ray light than Earth's entire aurora. These auroras are driven not just by particles from the Sun, but also by particles from Jupiter's moons, particularly Io. The volcanism on Io supplies a constant stream of charged particles into Jupiter's magnetosphere, and as these particles spiral along magnetic field lines toward Jupiter's poles, they create intense auroral displays. Saturn's auroras have a unique characteristic. They pulse at the same rate as Saturn's radio emissions, which are tied to the planet's rotation period. This suggests that Saturn's auroras are controlled by the rotation of the planet's magnetic field, creating a spinning curtain of light that sweeps around the poles once per rotation. This is different from Earth, where auroras are primarily driven by variations in the solar wind. Uranus and Neptune have auroras as well, though they are much more difficult to study due to the planet's distances. Their tilted, offset magnetic fields create auroral patterns that are unlike anything seen at other planets. On Uranus, the auroras don't occur near the geographic poles, but rather at mid-latitudes, because that's where the magnetic field lines converge. As Uranus rotates, its magnetic field wobbles, causing the auroral zones to sweep across different parts of the planet. Observing these auroras requires spacecraft or powerful space telescopes capable of detecting the faint ultraviolet emissions. The gravitational influence of the giant planets extends far beyond their immediate vicinities. Jupiter, in particular, has had a profound effect on the structure of the solar system. Its massive gravity has cleared out the asteroid belt, preventing the material there from coalescing into a planet. Jupiter's gravitational perturbations continually stir up the asteroids, causing collisions and ejections. Any asteroid that wanders too close to Jupiter is likely to be flung out of the solar system entirely, or sent crashing into the Sun. Jupiter also protects the inner solar system to some extent by deflecting or capturing comets that originate in the outer solar system. Comet Shoemaker. Levy 9 famously broke apart and collided with Jupiter in 1994, an event that was observed by telescopes around the world and by spacecraft. The impacts created massive fireballs and left dark scars in Jupiter's atmosphere that persisted for months. Without Jupiter's presence, some of these comets might have instead collided with Earth, with potentially catastrophic consequences for life. However, Jupiter's protective role is not absolute. Sometimes Jupiter's gravity can also send comets and asteroids inward, increasing the impact rate on Earth. The net effect is complex and depends on the specific orbital dynamics, but overall, Jupiter's influence has shaped the impact history of the inner solar system in ways both protective and disruptive. Saturn, Uranus, and Neptune have similar but weaker effects on their surroundings. Saturn's gravity influences the orbits of objects in the Kuiper belt, creating resonances where certain orbital periods are more stable than others. Neptune's gravity has an even more direct effect on Kuiper belt objects. Pluto, for example, is in a 3-to-2 resonance with Neptune, meaning Pluto completes 2 orbits for every 3 that Neptune completes. This resonance protects Pluto from close encounters with Neptune, even though their orbits appear to cross on a diagram. Many other Kuiper belt objects are also in resonances with Neptune, and these objects are called plutinos. The NICE model suggests that as Neptune migrated outward, it swept up many objects from the inner Kuiper belt and either ejected them or locked them into resonances. This migration sculpted the current structure of the Kuiper belt, creating the different populations of objects we observe today. The scattered disk, a region beyond the Kuiper belt, populated by objects on highly elliptical orbits, is thought to be the result of close encounters with Neptune during this migration. Giant planets can also capture objects as temporary satellites. Earth has had several small asteroids temporarily captured into orbit for a few months or years before escaping again. Jupiter and Saturn likely have similar temporary captures, though they're harder to detect. More dramatically, giant planets can capture objects permanently, turning them into regular moons. Triton's capture by Neptune is the most obvious example, but some of the smaller, irregular moons orbiting the giant planets might also be captured asteroids or comets. The irregular moons of the giant planets are a diverse collection. These are small moons, typically only a few miles to a few tens of miles across, orbiting on distant, inclined, and often retrograde orbits. They're thought to be captured objects rather than moons that formed alongside the planet. Jupiter has about 80 known moons, and the majority of them are irregulars. Saturn has a similar collection, with over 80 moons discovered so far. Uranus has 27 moons, and Neptune has 14, with more likely awaiting discovery. These irregular moons are interesting because they provide clues about the population of small bodies in the outer solar system at the time the planets were forming. By studying their compositions and orbits, scientists can learn about the types of objects that were available to be captured and the dynamical processes that led to their capture. Some irregular moons orbit in groups with similar orbital characteristics, suggesting they might be fragments of larger objects that broke apart after capture, either from collisions or from tidal forces. The regular moons, the large moons that orbit close to their planets in the plane of the planet's equator, are thought to have formed from disks of material surrounding the young planets. Just as the planets formed from a disk of material around the young sun, the moons formed from smaller disks around the planets. This is why the regular moons tend to be larger, orbit in the same direction as the planet's rotation, and have nearly circular orbits aligned with the planet's equator. Jupiter's 4 large moons, Io, Europa, Ganymede, and Callisto, are called the Galilean moons because Galileo discovered them in 1610. They're large enough and bright enough to be visible through binoculars, and they played an important role in the history of astronomy by providing clear evidence that not everything orbits Earth. Ganymede is the largest moon in the solar system, even larger than the planet Mercury. It has its own magnetic field, the only moon known to have one, and beneath its icy crust lies a subsurface ocean even larger than Europa's. Callisto is the most heavily cratered object in the solar system, indicating that its surface is ancient and has barely changed in billions of years. Unlike the other Galilean moons, Callisto seems to lack significant internal heat, so it never underwent the geological resurfacing that erased craters on the other moons. Its surface is a record of impacts stretching back to the early solar system. Saturn's largest moon, Titan, is larger than the planet Mercury and has a thick atmosphere, denser than Earth's. The atmosphere is mostly nitrogen, like Earth's, but also contains methane and a rich chemistry of organic molecules. Titan's surface has lakes and seas of liquid methane and ethane, rivers, and even rain, creating a hydrological cycle similar to Earth's water cycle, but at temperatures of -290 degrees Fahrenheit. The Cassini spacecraft deployed a probe called Huygens, which descended through Titan's atmosphere in 2005 and landed on the surface, sending back images of a landscape carved by liquid methane. Rounded pebbles and cobbles made of water ice covered the ground, shaped by flowing liquid over eons. Titan is thought to have a subsurface ocean of liquid water beneath its icy crust, maintained by tidal heating from Saturn, and possibly by the decay of radioactive elements in its interior. The combination of surface liquid, a thick atmosphere, and organic chemistry makes Titan one of the most intriguing locations in the solar system for studying prebiotic chemistry, and possibly even life, though the extreme cold presents significant challenges for any life as we know it. The diversity of moons in the outer solar system is staggering. Some are geologically active, some are ancient and cratered, some have atmospheres, some have subsurface oceans, some have rings of their own, and some have surfaces covered in exotic frosts. Each moon is a world unto itself, shaped by its unique combination of composition, internal structure, and interactions with its parent planet and neighboring moons. There are still many unanswered questions about the giant planets and their systems. We don't know exactly what the interiors look like, especially at the boundary between different layers. We don't fully understand the processes that generate their magnetic fields. We don't know why Uranus lacks significant internal heat, while Neptune does not. We don't know what triggered the collision that tilted Uranus. We don't know the full diversity of moons that exist, especially small, irregular moons that are difficult to detect. We don't know if the ice giants have large cores or fuzzy cores like Jupiter might. We don't know if there are undiscovered rings or if the known rings are stable or transient features. Future missions will help answer some of these questions. There are proposals for spacecraft to orbit Uranus or Neptune, similar to how Cassini orbited Saturn for 13 years. Such a mission would revolutionize our understanding of the ice giants, just as Cassini did for Saturn. Probes could be dropped into the atmospheres of the giant planets to measure composition, temperature, and winds directly. Missions to Europa, Enceladus, and Titan are in development or under consideration, aiming to study these moons in detail and search for signs of life in their subsurface oceans. Advances in telescope technology also play a role. The James Webb Space Telescope, launched in 2021, is capable of observing the giant planets and their moons in infrared light with unprecedented resolution. Early observations have already revealed new details about Jupiter's auroras, Saturn's rings, and Neptune's atmospheric storms. Ground-based telescopes equipped with adaptive optics can now produce images nearly as sharp as those from space, allowing detailed monitoring of weather patterns and long-term changes. The study of exoplanets continues to provide comparative context. Every new exoplanet discovery is an opportunity to test our understanding of planetary physics. Hot Jupiters challenge our ideas about planetary migration. Super-Earths and mini-Neptunes reveal planet types that don't exist in our solar system. Multi-planet systems with complex gravitational interactions push the limits of orbital dynamics simulations. Directly imaging exoplanets and measuring their atmospheric compositions will eventually allow comparisons between exoplanet atmospheres and those of Jupiter, Saturn, Uranus, and Neptune, revealing which features are universal and which are unique to our solar system. The giant planets also play a role in the broader story of stellar and galactic evolution. The heavy elements that make up the rocky cores and icy mantles of these planets were forged in the interiors of previous generations of stars. When those stars died, they expelled this material into space, enriching the interstellar medium. The solar nebula inherited this enriched material, and the planets that formed from it are repositories of this cosmic history. Studying the abundances of different elements in the giant planets helps trace the chemical evolution of our galaxy. On a more philosophical level, the giant planets remind us of the diversity and complexity of the natural world. These are places governed by physics, chemistry, and mathematics, yet they produce phenomena that seem almost magical. Diamond rain, hexagonal storms that persist for decades, moons with subsurface oceans warmed by tidal friction, auroras powered by volcanic moons, magnetic fields that wobble and flip. Each discovery raises new questions and opens new avenues of research. The fact that so much about the giant planets remains mysterious, even after decades of spacecraft missions and telescopic observations, underscores how much there is to learn. These planets are not static, unchanging spheres. They are dynamic systems, evolving on timescales ranging from hours for atmospheric storms to billions of years for their internal cooling. Every observation adds another piece to the puzzle, but the full picture is far from complete. For anyone interested in planetary science, the giant planets offer a rich field of study. The challenges are substantial, from the difficulty of sending spacecraft to such distant targets to the complexity of modeling their interiors and atmospheres. But the rewards are correspondingly great. Understanding how these planets work, how they formed, and how they interact with their surroundings is fundamental to understanding our solar system as a whole. And as we discover more exoplanets, the lessons learned from studying Jupiter, Saturn, Uranus, and Neptune will be essential for interpreting observations of gas giants and ice giants orbiting other stars. Schools teach the basics, the names of the planets, their order from the Sun, their approximate sizes, and perhaps a few standout features like Jupiter's great red spot or Saturn's rings. But the deeper story, the the one involving diamond rain, fuzzy cores, tilted magnetic fields, geologically active moons, and billion-year-old storms, is rarely told in classrooms. This is partly due to time constraints and the need to cover a broad curriculum, and partly because much of this knowledge is relatively recent, discovered within the last few decades by spacecraft and telescopes that have transformed our understanding. Yet these details matter. They turn the giant planets from abstract facts to be memorized into real places with ongoing physical processes, histories stretching back billions of years, and futures that will unfold over billions more. They connect planetary science to other fields like chemistry, physics, geology, and even biology, as the search for life extends to places like Europa and Enceladus. They inspire curiosity and wonder, showing that even within our own cosmic backyard, there are phenomena that challenge our imagination and our understanding. The gas giants and ice giants are not merely distant, cold, and inhospitable worlds. They are laboratories where nature conducts experiments under conditions that can never be replicated on Earth. They are archives preserving information about the solar system's formation. They are dynamic, evolving systems that continue to surprise us with new discoveries. And they are, in a very real sense, worlds full of wonders that most people never learn about in school.